Okay, today's lesson, we're going to be working on 8B, union and intersection, which usually leads into Venn diagrams and eventually two-way tables as well. Prerequisite knowledge for method stuff when it comes to probability. So here we go. Let's recap on some languages. So last lesson, we talked a bit on some terminologies, experimental versus theoretical probability. We did talk about a bit of the notations. Let's now look at a few more language or terminologies that we normally say when we're dealing with probability. A set. A set is a collection or group. Fill this in. Group that can include numbers, letters, or other objects. What's an example? Usually, and can you write this down as well? Usually denoted with a capital letter. So write in your own words, denoted with a capital letter. So it could be capital A, capital B, capital C. That represents a set. Oh, yes. Yep. So we use a capital letter to represent a set because usually when you're dealing with probabilities, there are different things that you'll be focused on. So by writing a description of each one, it takes too long. So we usually use a letter. But if you use a lowercase letter, that represents elements and doesn't represent a group. So how we do it, for example, if I was rolling a dice, right? So if I'm rolling a dice and I'm interested in, let's say, even numbers, then I might say capital E represents all the possible outcomes or results. When I roll a dice, I will get even numbers. Now, what numbers can I possibly get when I roll a dice for group E? Say it again. Good. So 2, 4, 6. And we usually use these brackets here. Anyone know what the name for these brackets? Yes. It's actually curly brackets, squiggly brackets, or the technical name is braces. Okay. So these bracer brackets, you only use them when you're listing items. Okay, now each of these items, there's a special name for it. Anyone know what those items, I call it items so that you understand my language, but in probability, there's a particular name for it. It starts with E. Anyone remember what it is? Okay, good. So this is a good refresher. It's called an element. So when you say element, it means an item within that group. So I just made up a group. I called E for even numbers. So use a capital letter. This is called a set. Sometimes called an event. That is what a set is. So a set is a collection or a group. We use a capital letter to represent, and it can include numbers, letters, or other objects. So for example, in this room, I could say the group of people, I might be interested in group B as the people who have a bandana or own a bandana, something like that. Okay, so it could be bandana with spots, bandana without spots. So you can list them out in words. It can be letters, numbers, or other objects. Okay. All right, so we now know what a set is. Sample space, which we kind of touched last session. What is a sample space again? Can I please have, let's go with Nishi. What's a sample space? Not sure? Not sure, Andrea? Outcomes, but specifically, it's all the possible outcomes in this particular trial or event or experiment. Yeah, so sample space is the total possible outcomes. So in the case of rolling a dice, the sample space would be 1, 2, 3, 4, 5, 6. Okay, so usually a language we say is all possible elements. Okay, AKA, also known as, there is a specific name, sometimes, especially in a Venn diagram, they might not call it a sample space, but they will call it the, anyone know this one? You might have seen or not heard it. It's that universal set. So remember, set means a group. But when you say universal set, which means universal group, it means that this will have all the entirety of what you can possibly have. So rolling a dice, universal set is 1, 2, 3, 4, 5, 6. Flipping a coin, the universal set is heads and tails. Yeah, so a universal set will have the entirety of all the possible elements, whereas a set doesn't have to be. A set can be anything you can choose. So you can say, so with rolling a dice, I could have made another group and I could have called it, I don't know, P, capital P, and that one contains the number 1. I could have the group C in the idea of rolling a dice. Group C could have what we call a null set. Means there's nothing in there. Okay? And in our case, a sample space or a universal set, which usually is written with the symbol, I'll talk about that symbol later. It has to be 1, 2, 3, 4, 5, and 6. Okay, so this is a universal set. In the rolling a dice, you have to have all the possible elements, but each and every one of these ones are possible sets. You can make up any set. I can make up another set and say just the numbers 1 and 2. I can make another set and just say all the odd numbers. Okay, so sets, think of it like a big picture. This is a universal set. And then all the sets within it is your capital letters. A, B, C, D. That's what essentially it is. Okay? And that's why this links very nicely into Venn diagrams, because instead of using a big oval, we usually use a rectangle for universal set. Okay? All right. So we've got sample space, which is also known as a universal set. Complement, we talked about last session, is an event that has elements I'm wondering why it's oh, that's right, it's the notation. How do you show that it is a complement? Little apostrophe. So I'll put a comma here. If the set is a complement is written with a dash. Dash to say that it is all the elements that is not a part of that set. So denoted as a dash. So is an event that has elements that is not part of a set. Okay? Null set, which I kind of just briefly touched before. Null set literally means there is nothing in it. Now, why do you think I can't put a 0 in that group? Because 0 is something. So it means that 0 is the element. So that's why a null set normally symbolized as either this, that's null, or the braces with nothing inside. Okay, so it's a set with no elements. Intersection and union, we've seen in the past. Intersection, which symbol is it again? Is it the hat or is it the smiley face? Hat. This is intersection. Union is easy to remember because it kind of looks like U for union. Okay, so this is union. And what it is, the difference between the two, intersection is when two sets have, what's intersection again? They have common. They have common elements, whereas union, when two sets have it's not really have, but it's more like you unite them together. So you group them together, yeah. Yeah, yeah. So you would say here, when two sets have, you can't even say have, actually. That's a bad say. I should fix my notes on that one. When two sets group elements, and is denoted by union. So think of grouping as adding. Common is probably the best word for intersection. So what do they both have the same? Two sets are considered mutually exclusive. Can I get a show of hands who actually have heard of the term mutually exclusive? Got 1, 2, 3, 4, 5, 6. Oh, it's not too bad. All right. For those who don't know, mutually exclusive literally means that they have no intersection, meaning they have nothing in common. So if they have nothing in common, essentially when we say group A and group B, so if group A intersects group B, we're essentially saying it's a null set. There's nothing that's in common between group A and group B. So what's an example? An example could be something like rolling a 3 and flipping a coin. So rolling a dice and flipping a coin, do they have anything in common? No. There's no chances that if you flip a coin that it ever actually is the same as you rolling a dice. Rolling a dice is always going to be different to flipping a coin. They have nothing in common there. Okay, so A intersection B does not exist. If you like it in a picture, this is how I can illustrate that idea. So let's say this is our universal set. Rolling a dice, you can have 1, 2, 3, 4, 5, or 6. So this is rolling a dice. So R for rolling a dice. And flipping a coin, let's call it F. You get it heads or tails. So in this universal set or sample space, I can have 1, 2, 3, 4, 5, 6, H and T. But do they have anything in common? No. Okay, they don't overlap, they don't intersect. So that's why these two groups, A and B, have nothing in common. So if I asked, is R and F, what does it have that's in common? Nothing. Okay, that's an example of when you're rolling a dice and you're flipping a coin, that's called mutually exclusive. Okay. All right, I know there's quite a bit of a terminology there, but these terminologies we use pretty much throughout year 11, 12 methods. So as I'm speaking to my year 12s, these are the language I would use, and the mathematics that we go through, the notations that we use is to illustrate that idea. Okay, so you just got to get familiar with that language. All right, copy that down. Reason why we need to know the language is because the two key diagrams or tools that we use to solve problems, especially at year 12 level, Venn diagrams and Carnot maps. I use both of them exclusively for different problems, but the one I use more frequently is the Carnot maps, which is also known as two-way tables. At a year 12 level, I'm teaching them to know when to use a two-way table. It's best for calculation, so maybe write this as part of your own notes. Two-way tables are best for calculations. So you're doing some maths calculations. Whereas Venn diagrams is best for regions or picturing the problem. Okay, so Carnot maps doesn't do well with picturing it. So what intersects with where's the union, what's the grouping together? So if I would explain to you, I usually use a Venn diagram, just like I have been so far, rather than using a two-way table. But if I teach you to solve a problem, you'll notice that I'll use two-way tables more because it's easier to calculate, but it's not easier to understand because you don't see the picture. Okay, so in that example, when I did that, I could have done that with a two-way table, but it would have been harder for you to understand. But with a picture, it makes more sense. That's group R, that's group F. But if you were to do it in a two-way table, it's harder to see. Okay, so Venn diagrams are great for visualizing the problem. Two-way tables are best for you to solve the problem. But they are actually the same. They're just two different things. They focus on two different things. So here we go. I'm going to highlight the regions. I want you to see how they link to each other. The region that most students know is this one. What's this region called again? In green. Intersection. This is the region where you say A intersects with B because they overlap. They have something in common. This is part of B and also is part of A. So they both have something in common there. Okay? Which actually represents in the table here. In the table when you list it out, A and B, this corner here represents the green region. Okay, so whatever you put in this region represents that corner there. A dash means not A. So let's look at this region then. What if I color this region in yellow? Anyone remember back in year 7 and 8? What's this region called? Specifically just the yellow. So I just want yellow. It's got A there, but not B. Doesn't have B in there. So that would be... Very good. A and not B. Was that what you were thinking? Good. Okay, so can you see that region there is outside of B, so it's not part of B. But not part of B is this entire region here. And A is only this section here. So where do they both have in common? It's where the yellow region is, which actually then represents this one. A with not B gives you the yellow region. What's interesting is if you add the green and the yellow region, what do you get? What group do you get? You get A, which is what this table shows. See, this table, if you add it vertically, that there should give you the total for A. Okay, which makes sense pictorially. Green and yellow shows that gives you the total for A. Okay, so this is why, as a calculation, had I wrote A intersect B plus A intersect B dash equals A, that would have been hard for you to understand. See what I mean? But this, as a picture, makes a lot more sense. So instead of me saying A intersection B plus A intersection B complement gives you A, that would have been very confusing for you to remember. It feels like a formula. That's why Venn diagrams are great to visualize the problem. This one's good for calculation. Okay? All right, so let's go with the next region. There are 4 regions in a Venn diagram. You have the green, the yellow, the next one here, I'm going to color it in blue. Just the blue region here. What is this region called, do you think? Can I please have someone else? Let's go with Sam. You want to have a go with this one? Beautiful. So this is not A, but it is part of B. And that blue region actually represents, so it is not A, but it's part of B. It is in this region over here. Okay. And then the last region, which one am I missing? What's the region that I'm missing? Yes, Andrea. Good. And that's the white region. Everything outside of these 2 circles. This is not A, intersection, not B, which I'm going to leave it as white here. Notice here, we then work out the table. Green plus blue should give me the total for B, which makes sense in the diagram. So this should give you total for B. Total for B complement. This is total for A complement. What do you think this corner would be then? What's the very bottom corner? Bottom right corner over there. Sammy? Yeah, and what's the name for the total overall again? Sample space or universal set. So this here represents the universal set. So I'm going to write here universal set. And that here in this whole entire box, it should represent every possible outcome based on our experiment or whatever the trial is. That's what that total should represent. So this is great for calculation. This is easier to picture what's happening. So some of the things that they get in year 12, as an example, if I told you to find A union B, there's a formula for one of this one, but you can probably see it with the color coding. If I want A union B, what regions am I going to be adding? What regions would I add? So if I want A union B, so in the problems they get, they might say, you know, like if group A was rolling, I don't know, a 3, and then B was something else, and they say group it together, A union B, they have to work out the total. How would you work this one out? Yes, Andrea. Ooh, so close. Let's go with that. So total A and plus total. So you're adding all of this plus all of this. Is that what you're saying? So total of A plus total of B naught to get A union B. So I want A union B. Which one is A union B again? What does A union B mean? Let's start off with that. What does A union B mean? Both A and B. So what's both A and B? This is, I'm going to draw it again. if this is A and B, then both A, so this is A, and then B, that's the region I want. Okay, so that's what A union B means. Now, in this table here, which regions would I be adding? Or did you figure that out, or did you know a formula? Okay, good. So that is one of the ways. So for those who don't realize what Sammy just said, she said total of A, which means green plus yellow, which is total of A. So I'm going to write here total of A. Plus, she said total of B. But notice if you do total of B, it's got green again plus blue. This is total of B. So the problem is that you're doubling up on the green region. That's why she said minus A intersect B. That's why then you get the total probability. So you minus the G. Can you see what's happening there? So she said green plus yellow gives you all of A. Green plus blue gives you all of B. But if you add those three together, you're doubling up on the green. So that's why you have to minus the intersection. So the rule is actually given at a year 12 level. This is called addition rule. So for those who don't know, write this in. Addition rule. They say A union B is equal to A plus B minus A intersection B. And a lot of kids just memorize that, but they don't know why. So I'm explaining why. So I'm showing to you visually. You can see if you want A union B, isn't it just all of A and all of B together? So you're adding yellow, green, and blue. But if you're adding yellow, green, and blue, it's just 1, 2, 3. There's only 3 regions there. So why is the formula A plus B? Because A represents green and yellow. B represents green and blue. Why do you have to subtract the intersection, which is the green section? You have to subtract it because you're doubled up on the green. Okay, so that's where that formula is coming from. And that's one of the formulas we use quite a bit in year 12 if the kids can pick up on that problem there. So the table shows you the calculations. You can actually just add these 3 regions, or you can use this formula here. Okay, so these 3 regions are simply A intersection B plus A intersection B dash plus B intersection A dash. You would still get the union as well. Okay, so you got these 2. That's what this exercise is going to be mainly about. You're going to work with these 2 diagrams or tools to solve problems. Okay, so when you're given a problem, you can try to do it in your head, but with these diagrams or tools, that should help you solve the problem easier. All right. Okay, team, let's do one example together so that you get a feel of how to solve problems using a Venn diagram and Carnot maps. What's this one? Oh, yeah. This might look confusing, but just out of curiosity, have you guys learnt what the letter N represents? Yes or no? Hands up for yes. Okay. Do you guys know the proper name for it? Starts with C. Okay, cool. It's called the cardinal number, but for most of us to understand it just means the number of elements. I have no idea. I just know it's called the cardinal number. Cardinal number means the number of elements. So they're saying how many items are there in this group. So A intersection B, they're saying there's 1 item. A intersection B dash, it has 3 items. A dash intersection B has 4 items. And then not A intersects not B has 2 items. Now the question's asking you to find A union B. Now that question might look hard. Now you can use the tools I just taught you and you should be able to figure out what A union B is. You can either picture it, when you use the table, fill out the table, and you should be able to get the answer. I'm going to pause the video and I'm going to get you to think for a bit. See if you can solve that simple idea. So this means number of items in A intersection B is 1. Number of items in A, group A, intersect not B is 3 items. 4 and then 2. What is A union B equal to? I'm going to pause, give you a minute and a half. It looks like this. So if you did a Venn diagram, whoops, let me go back again. If you use a Venn diagram, you would have seen this filling in the regions. So they said A intersection B is 1. So I just followed it. A intersection B is 1. A not B is 3. Not A but B is 4. And then everything else is 2. So if I asked you what is A union B, how many items are there? Well, you can see. There's 4 in A. And then there's this bit over here that's 4. So 3 plus 1 plus 4 should give you 8. Hands up, you got 8. Very good. So that was one way of doing it, so visualizing pictorially. Or you could use a table and do the same thing again. A intersect B, A intersect not B, A dash B, A dash B dash, and you would have got 1, 3, 4, 2. And if you add vertically, you get total for A, total for A dash, total for B, total for B dash. So I know the universal set should have 10 items. Okay. Union, you know that we're adding these 3 regions, so it's 3 plus 1 plus 4. Or you could use what Sanvi mentioned before. Total of A, so all of A, plus all of B, minus the overlap. Okay, so if you added this down, so 1 plus 3, plus 1 plus 4, and then subtract 1. So remember the rule that I just gave, A plus B minus A intersection B. That would have gave you 4 plus 5 minus 1, and you would have got 8 as well. Okay, so 2 ways to do it. Doesn't matter how. One's visual, one's good for calculations. So Sanvi's addition rule. So that addition rule, that could be useful, but if you know how to read the regions, either way you can get 8. 3 ways to get 8 there. So far so good? Alright. Alright team. Let's do one last example and then that's it for today. Flip over. Here we go.